In this video, we will explore how gravity works on Earth and also look at the concepts of weight and weightlessness. We have already seen expressions for the universal law of gravitation and Newton's second law, and we will now use these to work out the acceleration due to Earth's gravity. Let's say there's an object of mass m at the Earth's surface. Under the influence of Earth's gravity, the object will experience a gravitational force F, and according to Newton's universal law of gravitation, we can write this in the usual way of F equals gmm over r squared. There is also a force on the object due to the acceleration by Earth's gravity, and we know from Newton's second law that this force F will equal m times a. If we call this gravitational acceleration g, then we can write Newton's second law as F equals mg. Now, there is only one force acting on the object due to the Earth's gravity, so these two expressions must just be different ways of expressing the same force. Hence, these forces are equal, and we can write the two expressions for the forces as being equal. We can see that the mass of the object appears on both sides, and hence this mass, m, will cancel out, leaving us with the expression for the gravitational acceleration at the Earth's surface, small g, equals gm over r squared. If we use known values for g, the mass of the Earth, and the radius of the Earth, then we can calculate g. And we get the answer that g equals 9.81 meters per second squared. This is the gravitational acceleration at the Earth's surface. Note that this value of g is just a number. G is a constant. For any particular distance r from the center of the Earth, for example at the Earth's surface, g is constant. In fact, we can assume g is constant for reasonable distances close to the Earth's surface. To check this, let's see what the value of g is some distance away from the Earth's surface, for example, at the top of Mount Everest. We know the height of the mountain, so if we put in the numbers, we can calculate g at the top of Everest, and we see that g is very slightly smaller at the top of Everest than at the Earth's surface, by about 0.03 meters per second squared. So even at the height of Mount Everest, there is not much change in g, and this shows us that anywhere near the Earth's surface, we can reasonably assume that g is constant with a value of 9.81 meters per second squared. In many examples, when we have to use g, we can just approximate g to be equal to 10 meters per second squared, because that makes the calculations much easier, but does not really affect the result. So approximating g to be 10 meters per second squared is often done, but of course we can use the more exact value of 9.81 meters per second squared when we want to be exactly precise. Now let's talk about weight and what we actually mean by weight. We said that the force we feel on Earth is equal to mg, and it is this force due to gravitational acceleration that we call our weight. Weight and mass are not the same thing and are often used interchangeably in normal life, but strictly speaking, what we call an object's weight is only true at the Earth's surface. If we take the same object to the top of a mountain or to the moon, then its mass will still be the same, m, but its weight, mg, will have changed depending on whatever the value of the force of gravity is at that location. So in reality, when we measure something's weight, what we are actually measuring is a force acting on the object due to the Earth's gravity, and this force equals m times g. Weighing scales usually convert this force into kilograms or pounds in the display, but the scales are actually measuring a force. So next time you stand on weighing scales, just think that the number you are seeing on the scales is really a force, and it has been calculated from knowing the acceleration due to gravity at the Earth's surface. And that is all done using Newton's laws of motion and his universal law of gravitation. The expression for g, which we derived, is independent of the mass of the object, and this leads us to a very important conclusion. Since g is the acceleration due to gravity, our expression for g tells us that all objects accelerate at the same rate under Earth's gravity, no matter how big or small they are in mass, since the mass of the object does not appear in the expression. The common way of saying this is that all objects fall to Earth at the same rate. This is an extremely important conclusion. Before Newton confirmed this in his laws, Galileo had deduced the same result. There is an apocryphal story that Galileo dropped a cannonball and a musket ball from the top of the Leaning Tower of Pisa to demonstrate that all objects fall at the same rate. Nobody knows the truth of that story, but Galileo did certainly experiment on balls rolling along sloping tracks to be able to measure their acceleration due to gravity, from which he deduced that g was constant and independent of the mass of the body. So it is a universal fact that all objects fall at the same rate under gravity. But the reason we often don't observe this on Earth is because of our atmosphere. And so even though a feather and a hammer should drop at the same rate, the feather's descent is always compromised by air resistance, slowing it down, and hence it does not fall at the same rate as the hammer. If you were to remove all air resistance, however, like in a vacuum, then any two objects, no matter their size or shape, would then fall together. This has been demonstrated numerous times on Earth, but a famous demonstration was done on the surface of the Moon in 1971 by NASA astronaut David Scott, when he dropped a feather and a hammer. They both hit the Moon's surface exactly at the same time, wonderfully proving that all objects fall at the same rate.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the Moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Now let's look at another commonly used term, freefall. An object is said to be in freefall when it is moving only under the influence of gravity and there are no other forces acting on it. The planets going around the Sun, the Moon orbiting Earth are all in freefall. Space satellites and the International Space Station are also in freefall around the Earth because they are moving only under the influence of gravity. Things falling to Earth, like a skydiver who jumps out of an aeroplane but before they open their parachute, are commonly referred to as being in freefall, but actually they are not in freefall because they have air resistance also acting on them, which slows them down. This air drag is an additional force which acts on them on top of the force of gravity, which is why technically a skydiver is not in freefall. But if the drag is negligible, for example, if the object's surface area is really small, or if the object is only falling a short distance or a short time, then we can usually ignore drag and consider falling objects on Earth as being in freefall. So if we drop something from a building, for all practical purposes, we can say that the object is in freefall. This idea of falling from a building was actually central to a thought experiment which Albert Einstein did, and which led him to develop his general theory of relativity, and we will discuss that in a future video. Even Newton's legendary apple falling from the tree to the ground can be thought of as being in freefall if we ignore any air drag acting on it. This event, if it actually happened, is said to have been the spark for Newton developing his theories of gravity. He realized that the apple fell to Earth under the same principles that the Moon moves around the Earth, i.e., both are in freefall. Let's now combine these three ideas that we've just seen, that all objects fall at the same rate, Freefall and how weighing scales work, and in doing so we can demonstrate Newton's laws actually working in a real-life scenario. So let's say there is a person of mass m in an elevator which is stationary, and the person is standing on weighing scales which are on the floor of the elevator. This is a strange setup, but it will allow us to gain an insight into how the person feels their own weight and show us how we feel the effects of gravity and other forces. One thing to note, because forces are vectors, is that we need to keep account of which direction things are moving and which direction forces are happening. And so we will call the up direction positive and the down direction negative, just to be clear in our example. Now, we have already seen that the force on the person due to gravity will be given by mg, and this force, which we'll call Fg, will be downwards. Since the person is standing on the scales, the person is pushing down on the scales with Fg, but we know from Newton's third law about equal and opposite forces that there will also be a force upwards from the scales to the person, and we'll call this force Fs, for force from the scales. And force Fs acts upwards. One thing to point out is that when we feel weight, we are not sensing gravity pulling us down. What we are actually experiencing is the force pushing back on us from whatever we are standing on or that we are in contact with. So in this case, we feel the force Fs upwards coming from the scales to us. It is the force Fs that gives us our experience of what we call our apparent weight. So what the scales read is the value of the force Fs which the scales are applying to us. And we are going to see what happens to this force Fs as the elevator moves up or down. Newton's second law, F equals ma, says that the net force on an object, that is the sum of all forces acting on it, equals mass times acceleration. Let's put the forces Fg and Fs into this equation, and we get Fs minus Fg equals ma, taking the positive and negative directions into account. We can then rearrange this equation to get an expression for Fs, and we use what we already know, that Fg is just equal to m times g. So this is the expression we get. Hence, we finally can write down the expression Fs equals m times g plus a. This is the apparent weight that the person will feel, the force Fs. To give some numbers, let's assume in our examples that the mass of the person is going to be 50 kilograms and that g is 10 meters per second squared, just to keep things simple. And let's now look at some cases of what happens when the elevator moves in different ways, and we will use these numbers for our mass and acceleration in those calculations. When the elevator is at rest, then its velocity is 0, and hence its acceleration a is also 0. So we can then see that Fs equals 500 newtons, and this is the actual weight of the person that they will experience. And they will experience this same weight anywhere on Earth if they were at rest. Now, next, let's assume what happens if the elevator moves upwards at a constant speed of 5 meters per second. If the constant velocity is 5 meters a second up, then that means the acceleration is still 0 since the velocity is constant. We recall that acceleration is the rate of change of velocity with time, and constant velocity does not change, so acceleration a equals 0. Hence, the apparent weight, Fs, is still 500 newtons. So if the elevator is in uniform motion upwards, we don't actually feel any heavier. Your apparent weight stays the same as when you were at rest. If the elevator is accelerating upwards at 10 meters per second squared, then we can see that the apparent weight doubles to 1,000 newtons. And so the person does feel heavier while the acceleration is happening. This is the feeling we all get when the elevator first accelerates upwards. The extra force pushes us down towards the floor and we feel heavier. Sometimes people call this a G-force. In our example, the normal weight of the person is 500 newtons due to gravity, so feeling an extra 500 newtons would be the equivalent of another lot of gravity. We could say we were feeling a force of 2g. That is, we were feeling twice our normal weight. Now let's accelerate the elevator downwards. So A is minus 5 meters per second squared in this case. Fs now equals 250 newtons, so the person feels half their normal weight. And finally, let's accelerate the elevator downwards at 10 meters per second squared. This will be the case if the elevator cable broke and the lift began to free fall downwards. So A is now minus 10 meters per second squared. We can see that Fs now equals 0, that there is no force from the scales to the person, and so the person does not feel any apparent weight. The person is weightless and in free fall, along with the elevator and the scales. All are falling at the same rate, and in fact, whatever was in the elevator would be in free fall and falling at the same rate as everything else. This is why we get the funny feeling in our stomach when an elevator suddenly starts going downwards quickly, or when an aircraft suddenly drops due to air turbulence. What we are feeling is accelerating downwards and feeling a lower weight, or being in free fall and having no apparent weight at all. Lastly, in thinking about free fall, one thing to say is that there is a common misconception about what happens to things in orbit. We often hear that astronauts in space are weightless and floating around the International Space Station because they are in zero gravity. This is not true. There is still gravity even in space, and we can work out what the value of g is inside the International Space Station, and if we put the numbers into the expression for g, then it comes out that g is about 8.6 meters per second squared, or about 88% of what g is on the surface of the Earth. So there's still gravity at the International Space Station, but the reason the astronauts are weightless is because they, along with the International Space Station and everything in it, are in free fall around the Earth. So there is nothing pushing on the astronauts' bodies, no equivalent to the force from the scales, Fs, and hence there is no apparent weight that the astronauts can feel. They are weightless, but not because there's no gravity, it's because they are free falling around the Earth. So in this video, we have seen how to calculate the value of the gravitational acceleration g on Earth, and we can see that it has a value of about 10 meters per second squared near the Earth's surface. The value of g reduces with height above the Earth's surface, but not at a rapid rate. So for all practical purposes, we can assume g is constant near the surface of the Earth. We've also seen that all objects fall at the same rate under gravity, which is non-intuitive but borne out by Newton's laws. And finally, we have seen that we can get a feeling of being weightless if we are in free fall. We will extend how we use Newton's laws of motion in the next couple of videos, where we look at the properties of things moving on or near the surface of the Earth, and also how things move in orbit. But for now, I hope you've found this video interesting, and until next time, keep thinking physics.